Deep learning allows engineers to build models that can make decisions based on training data. These models improve over time using stochastic gradient descent. When a model gets big enough, the training must be broken up across multiple machines. Two strategies for doing this are model parallelism, which divides the model across machines, and data parallelism, which divides the data across multiple copies of the model. Distributed deep learning brings together two advanced software engineering concepts: distributed systems and deep learning. In this episode, Will Constable, the head of distributed deep learning algorithms at Intel Nervana, joins the show to give us a refresher on deep learning and explain how to parallelize training a model. Full disclosure, Intel is a sponsor of Software Engineering Daily, and if you want to find out more about Intel Nervana, including other interviews and job postings for Intel Nervana, go to softwareengineeringdaily.com/Intel. Intel Nervana is looking for great engineers at all levels of the stack, and in this episode, we're going to dive into some of the problems that the Intel Nervana team is working on. Ready to build your own stunning website? Go to Wix.com and start for free. With Wix, you can choose from hundreds of beautiful, designer-made templates. Simply drag and drop to customize anything and everything. Add your text, images, videos, and more. Wix makes it easy to get your stunning website looking exactly the way that you want. Plus, your site is mobile optimized, so you'll look amazing on any device. Whatever you need your website for, Wix has you covered. So showcase your talents. Start that dev blog detailing your latest projects. Grow your network with Wix apps made to work seamlessly with your site. Or simply explore and share new ideas. You decide. Over 100 million people choose Wix to create their website. What are you waiting for? Make yours happen today. It's easy and free. And when you're ready to upgrade, use the promo code SEDaily for a special SE Daily listener discount. Terms and conditions apply. For more details, go to www.wix.com/wix-lp/SEDaily. Create your stunning website today with Wix.com. That's Wix.com. Will Constable is the head of distributed deep learning algorithms at Intel Nervana. Will, welcome to Software Engineering Daily.
Thank you.
We've done a number of shows about the fundamentals of deep learning on several recent episodes. So if people are looking for an introduction to these concepts, there are some other episodes. They'll be in the show notes. We've covered recurrent neural networks and reinforcement learning and TensorFlow. We have not talked about how to implement these at scale because, we just haven't gotten there, but this gets to be a distributed systems problem. Eventually, the models and the data are big enough that you need to implement them across multiple machines. Before we talk about how to distribute the machine learning jobs across multiple machines, I want to talk a little bit about deep learning, even though we've gone over it in previous episodes. Give your description of the deep neural network data structure.
Okay, so I think of a deep neural network model usually as a computational graph where the nodes are fundamental math operations, and then the edges between nodes represent data. And usually the data is in the form of a tensor, which is like a multi-dimensional matrix. But it's also important to think about the neural network model kind of as just the stored variables or the weights, which are the values that we're trying to learn when we're training the model.
Describe the process of training that neural network.
Okay. So in general, you're just exposing the model to a large amount of data, and it's finding patterns in the data and updating its model or its weights based on that learning. And I guess I'll constrain the question a little bit by focusing on supervised learning. So in supervised learning, you're actually looking at a specific kind of data set where your data is divided up into examples or what the input to the model would be. So that could be images or text or speech data. And then the other half of the data set is labels or targets, which is kind of the correct answer for what you want the model to output given that input example. So to train a neural network in the supervised regime, you have to expose the network to a batch of both examples and labels, and then compute a cost function, which is a function that gives you a single number that represents kind of the correctness of the output of the model. So your model can actually output something that's shaped however you want it to be shaped. It could be a classification where you just say yes or no to some question, or you could be labeling like the category of an image or something like that, or you could even be identifying on a pixel level what that pixel represents, or putting bounding boxes around certain objects of interest. So those are the different kinds of outputs that are common to convolutional networks that are processing image data. And in any case, you need to boil all that output down to a single number expressing how right or wrong the neural network's prediction was compared to your labeled example. And then you use that cost number to feed into backpropagation, in which you compute the partial derivatives of the cost number to each of the weights in your network, and use that to drive making small changes to those weights that bring your whole model closer to something that performs well on new data.
And throughout this process of training a neural network, we are often using stochastic gradient descent. Give a brief overview for what stochastic gradient descent is and why it's useful for training a model.
Okay, so stochastic gradient descent refers to, we already kind of covered, the gradients are the partial derivatives to the weights. So the derivative of the cost function with respect to the weight, and that derivative tells you which way and how much you want to adjust that weight so that it makes a lower cost or a better guess on that data example. And then the stochastic part comes from the fact that instead of considering all of the data at once, you're considering a single example, or more typically a small batch of examples at one time, and making kind of a noisy update to your weights based on just those examples.
Mm-hmm. And we'll get into the discussion of this sample size of the data, but that term gradient, just to make sure some people who are moderately familiar with this topic, what does that term gradient mean? In stochastic gradient descent, we're refining this gradient. Explain what the gradient is.
Well, you can think of a gradient just like in the term of a hill or the slope of something. It's really just the derivative. And in this case, we're taking the derivative of the output cost function with respect to a specific weight or parameter we want to make an update to. And really, you're just finding a mathematical way to answer the question, if I change that weight by a certain amount in a certain direction, like if I increase it versus decreasing it, how does that affect the cost function output? So if the derivative is positive or negative, then I want to make the opposite signed adjustment to the weight so that overall that weight is producing one small contribution in concert with all the other weights towards the final output number that we're trying to reduce.
Mm-hmm. You mentioned that in stochastic gradient descent, we are taking a subset of the total data, the total examples that we have, and we're training the model with smaller batches of the data rather than the entire batch of data. Why do we want to do that? Why do we want to break our training examples into these smaller sets that we can train over time into the model?
I think there's kind of two different answers for that question. So one is more of a practical answer, and the other is a theoretical one. So the practical one is that you probably can't fit all your data into memory. Usually your data set's relatively large, and you can only afford to compute and update your model weights with respect to a small subset of the data. And the other reason, the more theoretical one, comes down to kind of optimization theory and thinking about the cost function as kind of a multidimensional landscape where you're trying to get to the lowest point in this landscape, thinking about it of going downhill in a more than 3D world, whether this landscape is convex or non-convex, and how many local minima versus a global minima there is. There are claims that using some stochastic gradient descent, choosing a certain batch size gives you a beneficial amount of noise that helps you kind of escape from local minima and find your way towards a better, or possibly the global minima or a better local minima. And I can't really go into any more detail than that because it's kind of over my head.
Okay. Well, in practice, how do you determine the right sample size of your training data to feed to the model one at a time? This is known as the optimal training batch size.
I think in practice, it comes down to a lot of experimentation. I mean, there's loose arguments based on theory that you want a certain batch size to help get the right amount of noise. But I think in practice, people experiment with batch sizes that are starting in the neighborhood of maybe 128 is a common batch size, and adjusting up or down based on either computational constraints or trying to get a better final trained model performance.
So how does the performance of statistical, so if you did statistical gradient descent versus if you could take all the training examples in batch, ignoring the memory constraints and whatnot, how much does this improve the performance or the accuracy of a model?
I'm not really sure. I think you could answer that question on a really small model and a small data set, but it's probably not possible to actually find out how the final model would perform if you did not use stochastic gradient descent, but instead you did batch gradient descent on a modern state-of-the-art data set, just because it's not computationally very possible to do that.
So if I have, let's say I have 1,000 training examples and I break it into 10 sets of 100 examples each, and I train the model with those sets of examples, and then if I were to permute them, or if I were to reconfigure those training sets, but if I were to take the same 1,000 examples, does it matter if I permute my subsets of data, if I mess around with that, does that change the model? Like, can I just take those 1,000 training examples, feed them in a certain order, and then take the same 1,000 examples and put them in again in a different order? Is that have any effect, or is it just going to overfit them more? What would be the effect of doing that, of taking the same sets of data and putting them in again, but in a different order?
So in general, we do want to shuffle our batches so that we don't end up with the same order every time. And we also want to make sure that there's some evenness to the statistics across all the batches. So like, to give a counterexample, we wouldn't want to put all the cat images in one batch and all the dog images in another batch. I think there's some strong theoretical reasons for why that's important, but I wouldn't be able to explain them.
Okay, so something I read is that in theory, stochastic gradient descent is a technique that can scale in effectiveness with both the amount of data and with the model size. Explain why that is.
Well, as your data size goes up, your batch size doesn't have to change, so you can keep processing a bigger data set in the same batch size of 128. You just take more training steps. Each training step operates on a fixed size batch. So in that sense, your fundamental iteration doesn't change. It's just that it's going to take more iterations and more time. And then as for the model itself, you may need a bigger model as you get more data, and you may need a deeper model, and you may need to adjust kind of the architecture of the model. But in general, you can continue to use the same fundamental algorithm of doing gradient descent with backpropagation. There are problems with really deep networks or with recurrent networks, where as you go towards the earlier layers in the network, like closer to the input side, the gradients can either vanish or explode, meaning essentially you start to lose the signal, and those lower layers would have trouble learning in that case.
We're talking about stochastic gradient descent in a single machine, basically. We're not really talking yet about the distributed world. So if we're just feeding subsets of our data set to our model in batches of a reasonable size, and we're just doing this sequentially, and we have the entire model represented on one machine, this is known as synchronous training. So explain what that term synchronous training means.
Well, actually, synchronous could refer to a form of parallelism too. So I guess the default implementation of stochastic gradient descent on a single node is inherently synchronous. So you take one gradient step for one input data batch, and update your model, and then you take another gradient step based on the next data example. But each time you do that, you're using the latest copy of the model. And that's important because you're actually computing the gradients with respect to the latest model and then applying them. So then once we get into parallelism, it's important to kind of either maintain that synchronous nature of the algorithm when we divide the work up across workers and figure out how to synchronize those workers, or we have to break from that algorithm and relax some of the constraints. And it actually has effects on how well the model converges.
Well, let's start to talk about that. So as we're breaking up, well, first of all, what's the motivation for breaking this up into multiple machines? Why would we want to parallelize and distribute our statistical gradient descent process?
So, I mean, if training a model on a single machine takes a week or, a month in the worst case, that sort of is a fundamental limitation. It's pretty hard to do research when your single iteration for an experiment is that long. So being able to break it up into smaller problems and work on them in parallel is extremely attractive to reduce training time.
For more than 30 years, DNS has been one of the fundamental protocols of the Internet. Yet, despite its accepted importance, it has never quite gotten the due that it deserves. But today's dynamic applications, hybrid clouds, and volatile Internet demand that you rethink the strategic value and importance of your DNS choices. Oracle Dyn provides DNS that is as dynamic and intelligent as your applications. Dyn DNS gets your users to the right cloud service, the right CDN, or the right data center, using intelligent response to steer traffic based on business policies, as well as real-time internet conditions, like the security and the performance of the network path. Dyn maps all internet pathways every 24 seconds via more than 500 million trace routes. This is the equivalent of 7 light years of distance, or 1.7 billion times around the circumference of the Earth. With over 10 years of experience supporting the likes of Netflix, Twitter, Zappos, Etsy, and Salesforce, Dyn can scale to meet the demand of the largest web applications. Get started with a free 30-day trial for your application by going to dyn.com/sedaily. That's dyn.com/sedaily. After the free trial, Dyn's developer plans start at just $7 a month for world-class DNS. Rethink DNS. Go to dyn.com/sedaily to learn more and get your free trial of Dyn DNS. So 2 approaches to doing this distributed neural network processing, the statistical gradient descent that we're breaking up into multiple machines. There's data parallel training and there's model parallel training. So broadly define these 2 strategies, and then we'll delve into how they work.
Okay, so data parallelism refers to splitting up the data batches across workers. So in general, each worker would have a complete copy of the model, and it would process a different subset of the data and compute gradients with respect to that subset of the data. But then before updating its model, it would exchange those gradients with its peers and come up with kind of a global gradient. And then every model would be updated so that as time goes on, you don't have n kind of completely unique divergent copies of the model, but you actually have one distributed model that's evolving over time. And then model parallelism refers to splitting up a model itself across multiple pieces of hardware. And sometimes you want to do that because one of your layers is actually too big to fit in memory, and you need to split it up across devices.
Okay, data parallelism divides up the data to copies of the model. So you take the model, let's call the model X, and we'll say we'll copy the model X to 2 versions of the model, X prime and X double prime. We'll just make these direct copies of the model X, and then we'll take 2 subsets of our training data. Let's say we have a massive amount of training data. We break it up into training sets A and B. We give them to X prime and X double prime, respectively, which are those are exact copies of each other. So now we have parallelized the statistical gradient descent because we have two training sets that we're giving to the same model, effectively, two copies of the same model. But now I'm going to have two different output gradients. So at X prime, after it processes the training subset A, and X double prime processes training subset B, they're going to have different output gradients. How do you resolve those two different gradients? You now have these two separate models where initially you only had one model.
Well, the short answer is averaging. So keep in mind that even when you're doing things on a single machine, if you're doing stochastic gradient descent, you're taking many batches of input data. So let's say 128 different images, feeding them through your network, getting 128 different gradients for every weight based on those 128 different images. But then you're only applying one update to those weights. So you're averaging those 128 gradients first and then applying them. So when we do distribution, we're still going to be averaging these gradients. And the question just, when we talk a little bit more about synchronous versus asynchronous parallelism and doing it synchronously, you can average the gradients before updating the model copy and keep the model kind of synchronized at all times. In asynchronous cases, we're actually going to be applying our locally computed gradients to a global copy of the model without waiting for other workers and introducing a race condition there.
Okay, so I'm not sure I totally understood all of that. So if I'm resolving X prime and X double prime by averaging their gradients, can you describe how that compares to what I would get out of the synchronous process? So if I were to just take the model X and process all of that data with stochastic gradient descent on model X, how would that end result compare to this process of making model X prime and model X double prime and then averaging it?
Okay, so let's just go with a specific example. So in the case with one worker, you only have model X and you do 128 batch size and you compute 128 gradients. Then you average those gradients together and you do a little bit more math to determine what the update you want to apply based on the gradient is, and then you apply the update. So your model takes one step based on those 128 images. And that's the complete iteration cycle. Now, if we break that up and we do synchronous data parallelism, let's say with two workers, so you have still the X and the X prime now, we want to keep the overall batch size the same so the algorithm doesn't change. So we're still going to process 128 examples per iteration, but we're going to make it so that each of our workers processes 64 now. So then each worker computes 64 local gradients, and then they synchronize with each other to exchange those gradients and take the average of all 128. And then each of the workers now has the averaged gradient, and they can apply that to their copy of the model. So both X and X prime take the same step, resulting in like X1 and X1 prime, which are the same model again.
And how does the fidelity of, or how does the quality of the model compare in those two approaches? Is it the same, or you don't get the exact same model, right?
Actually, I mean, barring the effects of rearranging floating point operations and having slightly different results as a function of that, the models would be exactly the same if you use synchronous data parallelism. So it's a technique that is very amenable to use without any adverse effects on training, but it runs into quick limitations in scaling, because if you don't want to change the algorithm and you want to stick with your overall same batch size of 128 per iteration, then it limits how many times you can clone the model out. If you're going to divide by 2 each time, then pretty soon you're getting down to, I mean, the floor is one example per worker, but even before you get that far down, the performance of a single worker on just a single image or a single data point may suffer, because each worker typically has a lot of inherent parallelism inside itself. So you may get the same iteration time doing 4 or 8 examples as you do doing one example on a worker because of vector processors.
This sounds like operations that you could also just prove mathematically, since it's a lot of like matrix calculations. And I know there's a lot of work in mathematics of people proving that certain matrix calculations can be rearranged with no problem at all. So you can probably get mathematical bases for what is parallelizable without any sort of perturbance.
Right. So in synchronous data parallelism should be mathematically equivalent to a single node training. But that's not the case anymore for asynchronous cases.
Okay, right. For the reasons that you just mentioned.
Right.
Yeah, okay. So we're talking about this in the abstract, and this is like it's pretty far beyond my proficiency for talking about it, but I'm doing my best, so I don't, some of this stuff is going over my head, but what are the engineering complexities of implementing this? Because we're just talking about it sort of broadly in whiteboard style, but what is involved in actually putting this into code?
Well, in practice, to do data parallelism in a synchronous regime, you need an all-reduce operation, which is kind of a collective communication operation where each of the workers exchanges their portion of the data with each other and computes the average, or at least computes the sum of the gradients so that they can locally compute the average, and does that whole operation very efficiently. And you need a fast network and a fast communication library to do that. And that's because during this time when you're exchanging and synchronizing gradients, all of the workers are blocked from doing any processing of new data. They can't start processing the next batch of data until they've applied the updates based on these gradients. So there's kind of a well-defined cycle. You do the forward pass through your network to produce an output from the data. Then you do the backward pass to compute the gradients from the output. And then you synchronize those gradients, update your model, and then you can start the next step. And there's no way to kind of start the next step without applying the update first. Hence, this synchronization being blocking progress.
So are there some frameworks that you're using or software tools? What exactly is involved, and how much of this do you have to write from scratch?
Well, people have written a lot of different frameworks to address this, and I guess we're developing our own frameworks. So we have Neon and ngraph, and other frameworks are out there such as TensorFlow or PyTorch or Caffe and others. And most of those frameworks, if not all, have some form of parallel training backend. And in some cases, they're more flexible. In other cases, they're more specific, where the training system kind of makes assumptions about how the parallelism will work and what parallel algorithms it supports. In general, for a researcher, it's typically easier and more flexible to use a single node solution because you don't have to lock down as much of your architecture and map it to kind of a specific parallel scheme, and you don't have to worry about all these details. But once you get to the point of scaling up a bigger product based on a neural network and also scaling up the size of your data set, it makes a lot more sense to invest in the engineering parallelize.
Okay, let's talk about model parallelism. We'll get back into the engineering stuff. I want to talk more about different frameworks and deployment strategies, but we should talk about model parallelism. So we talked about data parallelism, which is where you copy the entire model, you feed subsets of the data to each of the different model copies. Now, model parallelism divides up the models and then sends the same data set, the entire data set, to each subset of the model. And this is efficient because you don't have to have the entire model processing the data. You could just process all of the data on subsets of the same model. So how does the performance of model parallelism compare to the synchronous stochastic gradient descent that we discussed initially?
Well, model parallelism doesn't change things as far as being synchronous or being stochastic gradient descent. So you'd still be doing synchronous stochastic gradient descent when you start doing model parallelism. The difference there is that if you split one layer up across two workers, what that usually means is your layer has a weight matrix, And we're talking about a fully connected layer usually here. So a layer where there's a matrix of weights where one of the dimensions of that weight matrix matches the input shape of that layer. And to do model parallelism, we'd break that weight matrix across the workers. So now we have two fragments, I'd say, of size weights divided by 2 on each worker. And for the first such layer, you have to present all of the input data to both halves, do a smaller dot product to produce half of the output of the layer, and then you have to actually exchange those output halves so that you have the whole output of that layer so that you can feed it to the next layer. So you're actually doing synchronization and communication between each layer in forward pass as well as in the backward pass for model parallelism. And whether that's more or less efficient than data parallelism depends kind of a lot on the shapes and sizes of the network and the data, and basically the amount of values that you have to send in each of those synchronization steps.
What I'm realizing in this conversation is something that I didn't realize when I was preparing for the show, which is that when you're talking about data parallelism or model parallelism, you're talking about parallelizing one of these big models with lots of data. You're not necessarily talking about breaking this up into multiple machines, although you may want to do that. You have very good reasons for breaking this up into multiple machines, but you're just talking about on a single machine breaking up this complex and time-consuming processing strategy into different workers that may just be operating on the same machine.
Well, I think when I said workers, I'm thinking of multiple machines. Because typically we're able to completely utilize all of the compute resources in one machine without dividing the problem up into multiple workers.
Oh, okay. Then I'm mistaken again.
It's complicated.
Sure is. So speaking of that, I mean, we talked about some of the engineering complexities specific to data parallelism. What are the implementation difficulties for model parallelism?
From an engineering standpoint, it's really the same sets of challenges. You need kind of efficient communication implementations and a fast network. And I should also point out that you can do hybrid parallelism, and that's not uncommon to see in practice, where maybe if you have convolutional layers followed by fully connected layers, you might do data parallelism for all the convolution layers, and then switch to model parallelism just for the later layers in the network. And you can make that choice on a layer-by-layer basis just by looking at the ratios of compute to communication and based on the sizes of the weights and the network bandwidth that you have available between the nodes.
How are we choosing between these two approaches? What are the different applications that are good for data parallelism, and what are the ones that are good for model parallelism?
Well, in the case of a network that has a lot of convolution layers and a fully connected layer, usually because convolution is so compute intensive, it reuses the weights multiple times per processing an input image or example. It makes more sense to do data parallelism there. And then when you get to a large fully connected layer, it may be more beneficial to use model parallelism instead of data parallelism.
So you're looking at the entire neural network and you're allocating different you look at each different portion of the network and you say, okay, this portion would make sense with this parallelism strategy, and then this other portion would make sense with a different parallelism strategy, and you can just apply different strategies at different layers based on, I guess the main feature is, so what's the main decision point for whether you're choosing data parallelism at a certain layer or model parallelism?
It just boils down to coming up with the ratio of communication to exchange the gradients, for instance, to the amount of time spent computing locally. And that'll depend on the shape and size of your layer and your data. It'll also depend on the compute device and how many flops it has for that type of operation. And it'll depend on the network bandwidth and the memory bandwidth also that are available on that node and between the nodes.
How does that work in practice? Is that another process like the choosing the optimal sample size for stochastic gradient descent? Is that another one of these things where you just have to tinker around with it and eventually figure it out?
Yeah, so in practice, it's been done very manually in the past, and even to the point where it's cumbersome and if you want to optimize it well, you end up having to make changes at a lot of different layers in the stack, which makes your approach fairly fragile. And if you change something at the high level to your network architecture, suddenly you may have broken the optimizations that are at a lower level. And so recently there's been a lot of work into kind of automatically figuring out how to parallelize a neural network model and how to figure out where to place the different parts of the model as far as mapping them to compute hardware within a node or across nodes. And obviously it's an NP-hard problem to take a large compute graph and kind of like optimally map it to a compute system. But there's a lot of heuristics that you can do, and you can also take measurements of certain types of operations and take network bandwidth measurements to feed into that.
Artificial intelligence is dramatically evolving the way that our world works. And to make AI easier and faster, we need new kinds of hardware and software, which is why Intel acquired Nirvana Systems and its platform for deep learning. Intel Nervana is hiring engineers to help develop a full stack for AI, from chip design to software frameworks. Go to softwareengineeringdaily.com/Intel to apply for an opening on the team. To learn more about the company, check out the interviews that I've conducted with its engineers. Those are also available at softwareengineeringdaily.com/Intel. Come build the future with Intel Nervana. Go to softwareengineeringdaily.com/Intel to apply now. Right. So let's get back to the engineering discussion of this. So I've done a lot of shows about Kubernetes, and I've done shows about Mesos, and certainly shows about different AWS technologies. And these are systems that are eating away at what people used to have to know about distributed systems. You used to have to know how to deal with Byzantine fault tolerance, and then Zookeeper came around, and Zookeeper dealt with some of that, but you still had to do some stuff that was annoying. But then, now Kubernetes is here, and Kubernetes takes care of more of those issues. It abstracts away more of the difficulties. How much, when you're doing distributed deep learning, how much can you stand on the shoulders of giants and leverage those distributed systems solutions of the past?
Well, Kubernetes, for instance, is definitely a great ingredient for one of these systems, but by itself, it's not the entire solution. And how you leverage it even depends a little bit on the algorithm you choose. So, for instance, to address node failure, if you're in the synchronous regime, if you're breaking your model down into 8 workers and they're all synchronous with each other, if one worker goes down, then all the other workers are just going to stall and wait for it. So you'd really have to restore the entire cluster of 8 every time one of them fails. Even in that, you'd benefit from using something like Kubernetes because it just helps with bringing up 8 such machines and taking care of checkpointing them. But it's also difficult because a lot of the cloud infrastructure like Kubernetes is built on kind of this containerization model. And part of that way of thinking, I think, is that the hardware underneath doesn't matter and that the compute is kind of generic. And in this case, that's not really always true because model designers sometimes make very specific choices about their architecture that boils down to expecting to have a certain type of hardware with a certain amount of memory. And so your scheduler and orchestration platform has to be a little bit smarter than maybe in the average application about how it places things. And it also needs to be able to take into account network topology. So if it picks 8 random nodes in the data center, they may not be physically close to a switch, and so their communication latency is low or high. And you need to be able to you need to schedule jobs so that they can take advantage of a local high bandwidth network in order to be able to do these kinds of things.
Right. So for the internet scale services that we've been building for the last 15 or 20 years, Google popularized, let's just use commodity infrastructure. Let's just use cheap computers. All we need to do is serve search results to people. And now with machine learning, we're realizing, actually we need we can get much better performance, and it's worth investing if we get really custom, high-quality hardware, and it's leading to all this investment in new chips and new data center technology. Not that those types of investments weren't happening before, but it's certainly gone in a different direction because of machine learning. Although you were talking about the Kubernetes, for example, or the orchestration layer needing to have access to network topology and be able to intelligently select the right machine or the right type of infrastructure to do a machine learning job on, or a subset of a machine learning job on. How well are those abstractions baked into an orchestration framework?
Well, I know Kubernetes is designed to be extensible, so you can replace specific components like the scheduler just by designing your own and having it make API calls into the rest of Kubernetes. But I think out of the box, it's, at least in the last 6 months or so, it was missing some of the key components that we needed.
Can you talk more about what this software stack looks like? So, I know Intel Nervana is working on several different projects. So explain, for example, what your software stack looks like, what you're working with on a day-to-day basis.
Well, the framework that we developed that's open source is called ngraph. It's a graph-based neural network representation where each of the ops in the graph is a fundamental computation. You can build a neural network model as a function of kind of constructing these graphs. And so the graph is, I guess I would say, the middle layer of the stack. And above it, you have different front ends. So we have the neon front end, which is our own way of expressing concisely to construct a neural network model without having to think about all the different nodes in the graph. You can say, I want to have these layers stacked up and take care of the rest for me automatically. And it'll build the graph based on that description. And we have another front end to interoperate with TensorFlow. And we have other front ends planned for other frameworks. So at that level, our graph acts as a funnel to support this kind of rich ecosystem of different front ends that are out there. And then underneath the graph, we have different backends that compile the graph into something that can run on a specific compute platform. So we support CPUs, of course, we support GPUs, and we're also building custom silicon for deep learning.
Tell me about building the translation layers between those different interfaces. So, for example, you've got to have some sort of interoperability to interface with the stuff above the ngraph, right? That's the name, ngraph?
Yep, that's the name.
Yeah, so you've got to have a layer of interoperability with TensorFlow and ngraph and with whatever else is on top of ngraph. And then you've also got to have layers of interoperability between ngraph and the things below it. What's the standardization look like?
Well, it's a little bit tough to say that a standard has emerged because the field's evolving so quickly, but it's important to get to a level where you've got enough representation in the ops that you can kind of compose those ops to form anything you want to be able to form, so expressibility. And then on the other hand, you need a small enough set that it's manageable to implement kind of the handling of these ops for all the different backends. And then it's challenging too to make a decision sometimes where you want to express something like a softmax, which is a fundamental activation function that's used in neural networks, but which breaks down into a few different fundamental operations like exponentials and divisions and additions. And so you can choose kind of to represent softmax as an op, or you can choose to have just, a helper function that's called softmax, but really it just builds up like 5 or 10 graph ops that do something more fundamental. And that has implications because at the lower level in the back end, if you wanted to build, say, custom hardware to do softmax, you'd need some sort of a pattern match that identifies the fundamental operations and then reconstructs kind of a bigger operation out of them. Whereas if you had left it as a softmax operation to begin with, you'd be able to just feed that into your backend and say, here, just run this thing in your hardware.
And you mentioned some custom silicon. What is unique about the chips that are being built for deep learning?
I guess there's a couple of different angles. One is that they're designed to operate on fundamentally larger types of data in the form of tensors. So like a register is no longer a single int or a float. It's a whole tensor or a fragment of a tensor. And another one maybe is the number representation. So specifically zeroing in on the kinds of number representations that are important for deep learning. Using floating point 32 or 64-bit is important for scientific compute, but for deep learning, at each part of the network, such as the weights themselves or the updates to the weights and the gradients or the activations, you can get away with compressing down to smaller number representations. And doing that allows you to get more memory bandwidth or get more out of your memory bandwidth and pack in more compute.
So is the goal in your mind, is the goal for the average machine learning developer for this stuff to mostly be abstracted away and they would do all of their work at the higher level framework interface? Or what are the areas where you think the engineer will actually have to interface with their machine learning algorithms?
I think the pie in the sky idea that everyone has is that you work with these high level frameworks and define a pretty simple and concise neural network model, and you're expressing just the math you care about, and you don't worry about any of the stuff underneath. So you have compilers that sort of automatically figure out and solve all these other problems. But it's just that they're really quite hard problems. So in the field, there's a lot of evolution in developing heuristics and automating certain parts of it. But there's still kind of a lot of manual involvement to make sure that the model you build ends up mapping the way you wanted it to into hardware and runs as fast as you can.
So in practice, are people having to duck down beneath the higher level framework to do some specific tuning or some specific configuration today?
Yeah, definitely. And maybe it's already starting to turn. So maybe people are, because two things are happening: faster compute platforms are coming out and the software is getting smarter. So at some point, I guess more and more people are able to just live with whatever comes automatically out of using these high-level frameworks.
So we've talked about basically two different things here. We talked about building stochastic gradient descent models effectively. We've talked about how to parallelize them. And then we talked about some of the technology that's being built to allow people to do this under the hood. And we talked about the software at the higher level that people are using that translates into the lower level things like ngraph and then eventually to the hardware. So let's combine those two branches, and maybe we could talk through a simple example. Like, let's say you're building a massive neural network that identifies cat pictures, for example. We just got a bunch of pictures and we're trying to train it to identify a cat. Kind of give us an end-to-end picture for how that works in the naive, non-parallel, the synchronous way, and then how that would be parallelized, and kind of explain where the different frameworks and the different layers of abstraction fit into that.
Okay, so I think the main starting point for academics or for people who are just trying to get up to speed in this field would be to download a data set such as ImageNet, which is 1 million images in 1,000 different categories, where your cat is one of the categories, or maybe specific cat breeds even. And then take that data set and use it on a computer to build a model and train the model and see how it performs, and then maybe tweak the model architecture and see if they can get it to perform better. And then I guess if you sort of extrapolate on that to collecting your own data and getting and scaling up, you start to have to build your own infrastructure even to collect data and to be able to hand label it and farm that work out somehow. And then at some point, your training time is going to be too much to bear if you're using a single computer, and you end up switching to a kind of a distributed system.
Right. So what happens on the actual algorithmic front? So when I'm going into the model parallelism or the data parallelism, how do I know that I need to parallelize my algorithm? What starts to break down, or am I just trying to speed things up? And then where am I actually doing that? How am I applying that? Is there like a setting that I can just, flick on my machine learning framework to make this data parallel, or maybe give me a description for how an engineer would do that?
Okay, so yeah, in general, it could be a little bit of a hard problem to figure out how to parallelize any model as best you could. But in practice, one easy way to start is by using kind of the motifs that are already common. And so a lot of frameworks such as Neon has a built-in multi-GPU backend where if you're already building a network out of convolutional or recurrent layers or fully connected layers, you can first run it on a single compute device and then automatically switch to a multi-GPU backend that does data parallelism for you. And you won't get any weird algorithmic side effects because the algorithm won't change and it's pretty much automatic. But your scaling is pretty limited because you're trying to keep your overall batch size the same and you're dealing with fundamental limitations of like how many GPUs you can stick in a single server. And when you want to start to scale up a lot more than that to like hundreds or thousands of nodes, you probably need to start using a different approach like an asynchronous system with a parameter server. And then your algorithm does start to change and you get some side effects in terms of how accurate the final trained model actually is, and it gets a little bit more complex.
Okay, well, let's zoom out a little bit. You're working at Intel Nervana. You worked at Nirvana Systems, which got acquired by Intel. How does Nirvana Systems fit into Intel's strategy?
Well, we've just formed a new business unit at Intel called AI Platforms Group. So AIPG is a high-level business unit that's tasked with the vision for AI at Intel and includes all of the stuff that came from Nirvana, as well as trying to leverage and develop a common vision around all the different AI products that Intel already has.
And how do you see that evolving as a business? Do you think this would be like a cloud service that would be offered to engineers, or is that not public yet, or what has been discussed as far as products?
Yeah, so we're definitely advancing on a couple things in parallel, including building silicon and building a cloud service. But it's still kind of to be determined how our business model is going to evolve and how the cloud service is going to play in.
Yeah. So what does your work look like on a day-to-day basis? So what kind of stuff have you been working on personally?
So I'm focusing right now on sort of adding components to ngraph to support parallelism strategies, specifically synchronous data parallelism, but longer term, a variety of other techniques as well.
And what are some of the problems that you're solving creating synchronous data parallelism, for example? Like what's a bug or an issue that you ran into recently that you had to solve?
Well, it can be anything from trying to debug the modifications we do to the graph, sort of like compiler type code, to the low-level multi-processing and communication library code that deals with pointers and buffers and synchronization and race conditions and things like that. You end up debugging the full stack, and you're often not sure whether your bug comes from sort of a really high-level problem in graph model or some kind of a low-level bug in some other part of the code.
All right, well, to close off, we've been talking about essentially how to scale deep learning. And as time goes on, we're going to need to scale it because we have self-driving cars coming down the pike. We've got drones, all these IoT sources of massive amounts of information. And these are all opportunities for deep learning. So we will need to scale deep learning. Are the present techniques that are being pursued, do you think they are good enough, or are we just waiting for kind of the engineering implementation of what we understand to be effective enough theoretically, or are there still some theoretical hurdles that we need to figure out how to accomplish?
Well, the theoretical hurdles, I think, are plentiful in terms of the field itself being based on maybe some poorly understood theory, and people often say it's a marvel or a breakthrough of engineering over theory. In this case, getting deep learning to work so well, despite maybe not having a solid justification for why. But the current techniques are continuing to evolve in a good direction based off of engineering, and some theoretical work is producing promising results as well. I think one of the interesting things that we can expect to see coming out soon is that with our custom silicon, we can actually design in a lot more of the distribution. So the custom communication fabric between our chips and our software stack can be tightly integrated to make it so that you can scale your models up more easily without kind of as much cognitive load on the developer.
All right, well, thank you for coming on Software Engineering Daily. It's been a real pleasure talking to you about distributed deep learning. This was a topic that was out of my comfort zone, so I hope I did a reasonable job as an interviewer.
Oh yeah, it was my pleasure. This is my first time to be interviewed on your podcast, and it's been a lot of fun.
Okay, great. Well, thanks, Will. You have a full-time engineering job. You work on back-end systems or front-end web development. But the device that you interact with the most is your smartphone, and you want to know how to program it. You could wade through online resources and create your own curriculum from the tutorials and the code snippets that you find online, but there's a more efficient option than teaching yourself. If you want to learn mobile development from great instructors for free, check out CodePath. CodePath is an 8-week iOS and Android development class for professional engineers who are looking to build a new skill. CodePath has free evening classes for dedicated, experienced engineers and designers. I can personally vouch for the effectiveness of the CodePath program because I just hired someone full-time from CodePath to work on my company Adforprize. He was a talented engineer before he joined CodePath, but the free classes that CodePath offered him allowed him to develop a new skill, which was mobile development. With that in mind, if you're looking for talented mobile developers for your company, CodePath is also something you should check out. So whether you're an engineer who is looking to retrain as a mobile developer, or if you're looking to hire mobile engineers, go to codepath.com to learn more. You can also listen to my interview with Nathan Esquinazzi of CodePath to learn more. And thanks to the team at CodePath for sponsoring Software Engineering Daily and for providing a platform that is useful to the software community.